Hello, today I'm gonna talk about the ways in which we learn. I would like to reconcile the fact that throughout centuries we've seen a relentless march of science. We've seen tremendous progress in science, but at the same time we also see up to this day that people repeatedly fall for bad theory, bad science, and unsubstantiated claims. Okay, so in case you wondered, this is the way we learn. And this is in fact the way all data processing systems learn. So first we have some prior belief about the likelihood that a certain theory A is true. This is our prior belief. And there we are updated with information. Information arrives, I call it omega, and the likelihood to obtain this information, given that theory A is true, is the strength of the update. Okay? If this sort of information is likely given theory A, we're going to get a big update. If this is unlikely, we get a small update, and our posterior, in the end, will be similar to the prior. So, it depends what sort of information we get. If we get meaningful information, we should be able to strongly update our prior belief. If we only obtain hardly informative set of evidence, then maybe our update is going to be small. Okay, and that's all divided by the probability that this sort of information can be generated altogether. Again, sometimes you split this probability using the total probability theorem, so that you can say that the probability of this sort of information to arrive to you is the sum of the probabilities of this information arriving if theory A1 is true, this information arriving if theory A2, A3, A4, and so on is true, and until the theory AN. So this presumes that there are n theories which are competing, and they differ in the likelihood of generating this information omega. So, okay, if you prefer some distributions, you could also think about distributions. So the distribution of a certain x, which is a certain phenomenon in which we are interested. We don't know what that is, but we have some prior belief about this. This is our f of x. But then there comes the information omega. Information updates our prior belief, and so we get the posterior belief conditional on the information that we have. All right then, so what are the possible problems in our learning? Okay, there are two major problems. First of all, that's the issue with our data processing algorithm that works in our heads. And the second one is the information that we are faced with. As far as our brains are concerned, we have for sure a set of biases in our thinking, and this interfere in the most efficient way, with the most efficient way we could potentially learn. So first of all, we may overestimate the prior. We may be too convinced that our prior knowledge is adequate. Okay, so it may be the case that our mind is already made up, and in that case, it's very hard to present evidence that would convince us to change our minds. So that's the first thing. Okay, learning is much easier if you don't have a strong view in the first place. Ideally, if you have a tabula rasa, you have absolutely no idea, then you update your information most efficiently. Then gathering information is costly, so we may fail to identify the set of all possible theories, a set of all possible processes that could give rise to the data we see. And so we may become overconfident. We may overestimate the probability of this data that arrives to us conditional on the theory that we are interested in. Okay. An additional point is that we may undervalue parsimonious specific theories and overvalue vague and general theories, which can be consistent with various sets of information. Like, to take an extreme example, if you have a theory that says everything goes, then no matter what kind of information you get, you reinforce the truthfulness of this theory. Just, okay, whatever data you get, it's consistent with a theory that says everything goes. And this is particularly important if the data that we see is noisy. So if the data that we are faced with is not just pure signal that presents the true symptoms of the phenomena in the world, but if the data also features noise, which does not represent the true world, then if you have a sufficiently vague theory, it can be made consistent both with the signal and with the noise. Whereas parsimonious theories will be more sensitive to noise. The second point is our exposure to information. In this regard, it's most critical to observe that information gathering is costly, that reaching out to get more information takes time, takes effort. We don't have unlimited resources to do that. We need to make decisions. And that is a problem, especially if we have a strong confirmation bias. So that means we would be tempted mostly to look for information that would corroborate the theory that we have in mind and not spend too much resources on gathering information which could potentially falsify the theory. So that's one cognitive issue. Another one is that we may have already a strong view, which means we may underestimate the amount of information we need altogether, because we may say, well, but we basically have already made up our minds, and there is no point in putting more information into the process if there is not much to be updated. What I'm particularly interested in is the progress of science throughout the centuries. And clearly, if we look at the human history, if we look at the history of the human civilization, we see the tremendous technological progress, we see the tremendous achievements in basic science, our understanding of physics, of chemistry, of biology, of psychology, economics, whatever, has increased tremendously across the centuries. Therefore, we could also have progress. We could also achieve progress in engineering, in creating new goods and new production processes, and improving efficiency in our operations and so forth. So this tremendous progress has been great for the development of the human civilization. On the other hand, there is always a tendency among people to disbelieve certain scientific findings and question them, which is good, but also to fall for unscientific, unsubstantiated claims purely on faith and on trust in other people, in other people's beliefs. And we may also fall for bad science, for illogical pseudo-proofs, pseudo-arguments, and for claims that are based either on no empirical evidence or on wrong evidence, on noise rather than the true signal. In particular, in the digital era, where each of us has access to amazing amounts of information over the internet and also has the possibility to create new information and bring it into the internet. We are faced with a deluge of information which creates a filtering problem. As I said, filtering is costly, information gathering is costly, and the more noise is there, the more costly it is to filter the signal from the noise. So let me now again walk you through all the elements of the Bayes theorem to indicate where the biases and the cognitive issues may come in. So first of all, let me start with the prior. Okay, if you look at this prior, it can be inflated and can be overestimated if you have been subject to indoctrination, if you believe in certain claims without evidence. So if you've been faced with dogmatic statements or erroneous proofs of certain statements. So for example, you could think that there is proof for the truth of the Bible, but in fact the proof for the truth of the Bible is in the Bible, so that's not a valid empirical proof, right? And so on. So you could bring in certain examples like this, and that all emphasizes how inflated your prior can be. Secondly, if you look at the updating process, here the key thing is that we are faced with a choice of two ways of proceeding, and only one of them is rational. Okay, one of them leads to efficient updating, and that is the route of reductionism, Occam's razor, and looking always for theories that are as specific as possible so that they would has as high as possible this possibility of generating data. Because if you have a very specific theory which is true, you have a very high probability. If you have a specific theory which is false, you would have a low probability, right? Because it will for sure generate very specific data pattern, only that it would not be the same pattern as you see from the real world. Okay, but if you have a vague theory, it will be consistent with a lot of data patterns. And this is particularly aggravated if data is noisy, because vague theory can be easily made consistent with noisy data, and specific theory would not explain the noise. So you would have trouble in identifying the true theory here if your data is noisy. Here I think the best way to put it is that we have a dichotomy. Either you follow reductionism or you fall for pseudo-profound bullshit. Okay, you fall for complexity and obfuscation. You could have pseudoscience, which uses clever sounding words, complex sounding theories, or complex sounding arguments. They may be even internally inconsistent, but above all, they are not empirically falsifiable. They are too broad to be of practical use in discriminating across different theories. So this is the problem that we can have here. We may confuse scientific vocabulary with science, and we may just not understand that certain logic of proof is flawed. And now this. Here I said already, we have a filtering problem. We have confirmation bias, which makes us look for information only in specific, not in all the relevant places. We have also now the internet and algorithms which reinforce our confirmation bias, because it sees we like certain sort of information, so it feeds us with even more of this sort of information, but not the other ones. So this can lead to the confusion of simplicity and specificity. So you may think, okay, we need something simple, as I already said, reductionism is great, so why not reduce everything to something very, very simple? But if it's simple and it's false, then it doesn't solve a problem. Okay, so you need to look for the information in all relevant places, which can be hard, and it's for sure costly. So after all, how to avoid these pitfalls that I already mentioned? The simplest thing to say is keep rational. Remember to thoroughly check your sources. Believe in peer-reviewed science. Don't believe in claims without substantial evidence. Try and look for specific explanations. Don't be satisfied with vague, imprecise statements which are hard to falsify. And don't be satisfied with overly simple explanations which ignore evidence. The extreme example of claims without evidence are religious claims, religious texts. They are basically all based on dogma, on revelation, and don't provide compelling empirical evidence for being true. Now, if you think about specific but false theories which overtly dismiss a lot of true evidence, I guess here the champions are anti-vaccination movement, flat earth movement, what else? Climate change denial, evolution denial, I guess. If you think about pseudo-profound bullshit, I guess here you can think of a few champions, and one of them is clearly Deepak Chopra. And there is even a great website on the internet, wisdomofchopra.com, the enigmatic wisdom of Deepak Chopra, and it randomly generates claims that have been never made by Deepak Chopra, to make sure, but these are claims that sound as if he could have said that, and they are the perfect examples of what I mean by pseudo-profound bullshit. Okay, let me generate some random quotes. The mind is the ground of species-specific knowledge. Okay, I'm clicking receive more wisdom. Kittens are birds. The world is mirrored in formless images. Receive more wisdom. Hidden meaning is the path to personal belonging. Oh, that's great. Quantum physics complements visible self-knowledge. So you know where this is heading. Yeah, especially if you think about such theories like quantum theory. People don't understand that, so it's very easy to create something that uses these complex scientific terms out of their actual scope of application and sound seemingly wise. Okay, to conclude, eternal stillness is a modality of species-specific sexual energy. Your heart creates an abundance of molecules. Thank you. Bye. Like, share, subscribe, all the usual stuff. Thanks.